Bernoulli's equation deals when you have a change in speed, also a change in height. We'll break it down to two parts. We'll do the change in speed first. This coffee is horrible. Again, let's take change in speed. So we're not changing the height. We have a hose laying on the ground. The only way to change in speed if we go from bigger to a smaller or smaller to bigger. Now, if you picture the water coming in, this like a strip of water here. You're watching that piece move. It's moving forward. It's moving that direction. It's going to have an equivalent piece right here. Well, if we open the hose on this end, we'll get a force pushing this way too, which is the pressure, the air pressure. Let's call it F2. Thickness of this, delta X. Work is what? Force times distance. That's what work is. Change in work, it's force times the change in distance. So if I move that piece a little bit forward, that little strip that you see there by delta X, the amount of work is the force that applied to it times delta X. Well, let's look at the force. Early today, first thing we wrote, where was it? Review of last class. We said pressure equals force over area, or force equals pressure times area. Remember that one? So if I replace the force by pressure times area, so this is, let's do it this end, this is force 1. So change of work 1 is force 1 times delta X, or delta X1. Let's leave in terms of each one. So force 1 is going to be pressure 1 times area 1 times delta X1. Area times the distance is really the volume. So that's pressure 1, that's a 1, and this is times the change in volume 1. That's the work done by this piece. Work that's going to the right, that's positive work. Let's say the work, the way I do the picture, the work done by the second force, since it's going to the left, that's negative F2 times delta X2. That's pressure 2 times area 2 times delta X2, which is negative pressure 2, area 2 times delta X, that's the change in volume 2. Well, the change in work in this case will be W work 1 minus W work 2. That's the difference between the two of them. That's the difference, the change in work. And that will be P1 times delta V1 minus a negative P2 times delta V2. Minus a minus will make it a plus. We know if that's water, actually, if you do this as water, it's going to be pushing it in which way? If this is water moving, this water will be moving that direction. But the way I drew this, I drew it going that way. Right? So it would be a negative. But in real life, if that was a hose, you turn it on, this water is going to push in that direction, this will go in that direction, this will be a negative sign. But the way I drew mine, I drew it that way. So what? So if I change the direction of that, this becomes a minus. Everyone see that? If that equation, if I go back and redraw that, so it depends how you draw the picture there. And if this is force 1, and you make this go in that direction, force 2, then this equation, the change of work will be P1 delta V1 minus P2 delta V2. Because notice the difference between them, and both will be positive work, not negative. So be careful how you draw them. Sometimes they're misleading there. Well, we also know work is changing kinetic energy. And kinetic energy, if you remember, it's 1/2 mv squared. I'm trying to derive an equation for us. I like that better, actually, because if you push in the water. So the change of work is P1 delta V1, I'm going to use that one, minus, because in real life, that's if you're pushing it that way, it's going to go in that direction, P2 delta V2 equals the change in kinetic energy. 1/2 the mass is rho times volume 1, just in case you have different liquids there. 1/2 m, that's volume. This is going to be confusing here. That's the velocity squared. Minus the change in the other one, 1/2 rho 2 volume 2 times velocity 2 squared. And I think we got the equation. Now we just got to rewrite that. If you take this equation, rewrite it nicely, P1 delta V1 minus P2 delta V2 equals 1/2 rho 1. Instead of V1, how about change of V1 times the velocity squared, so you know velocity and volume there. How about delta V here? It looks nicer when you do it that way. Okay. Well, the amount of volume that's going to go in is going to equal the amount of volume is going to come out. If it's a hose and there's no leak in it, whatever you push in from that end is going to come out of that end. So delta V is going to be the same for all of them. Delta V1 is going to equal delta V2, so I can just drop them out. So I have pressure 1, I should have this backward, final minus the initial, isn't it? Final minus initial? Final minus initial. It's V2 is the final, the change in kinetic energy is the final minus the initial. This is the final, that's the initial. This is coming through the hose, final minus the initial. So when you do the math, what are you going to have? This is a minus, that's a plus. P1 equals, let's put the P1 together. When you bring this to this side, becomes plus 1/2 rho 1 V1 squared equals, move the P2 to this side, that's pressure 2 plus 1/2 rho 2, that's rho here, times the velocity square. And that's Bernoulli's equation I was trying to derive there. That's the equation I need. No change in height. The pressure on this end plus 1/2 rho 1 V1 squared equals the pressure on that end plus 1/2 rho 2 V2 squared. In a few minutes, we'll give you a change in height. And again, why this is minus a plus, it's the final minus the initial. When you think about the water coming in, going through this hose, this is the final, right? And this is the initial. It's coming in, it's going to continue, that's the final. So it should be this one minus that one. 1/2 the mass times the velocity square, that's the final velocity square, minus the initial 1/2 mass times velocity initial squared. Final minus the initial. Move them around, put the P1 together, you end up with the equation. Let's take an example on that and see how that works. That's called Bernoulli's equation. This is constant height. We use this when the height is constant. What happens if the height is changing? That's a different story. But if there is no change in height, that's what's going to happen. Here's an equation, problem, an example. Let's see. The previous example that we just did here, we have the hose, the nozzle, 9.6, I think it was, diameter was 9.6. It was moving, this velocity, if I remember, was 1.3. It goes to a smaller nozzle. Diameter equals what? Was it 2.5 centimeters? What was the velocity? We did that. We calculated the velocity. We found out V equals what here? 19, was it?
19.2.
Yep, 19.2. That's the previous example. Now, let me add to that. Let's assume the pressure from this end, the pressure, P1 is 350 350 kilopascal, PA, not atmosphere, kilopascal. What is the pressure of the water coming out of this? What's the pressure? Bernoulli's equation says P1 plus 1/2 rho V1 squared equals pressure 2 plus 1/2 rho V2 squared for constant height. Pressure 1, 350,000. 1/2 rho is 1,000, it's water. Velocity squared, 1.3 squared, equals pressure 2 plus 1/2 times 1,000 times velocity squared, which is 19.2 squared. Oh, forgot to turn on. Clear. The left side is equal 350,845. The right side equals 184,320. What is pressure 2? 350,845 minus that number equals 166,525. Basically 167 kilopascal. It's moving faster here. What's the pressure? Lower. There's a joke in physics, not really funny unless you're a physics person, you think, oh, this is really funny. Two guys, one is named speed and one is pressure. Low speed, high pressure, low speed, high pressure. Told you it's not funny. Low speed, high pressure. High speed, low pressure. So when things are moving fast, high speed, you have low pressure. When things are moving slow, low speed, you have high pressure. Now we use that logic on airplane wings. They were designed that way. The wings on the airplane designed like this, where the wind on the top of that moves much faster than the bottom. So since it's moving faster, you have low pressure here on the top. And since it's moving slower on the bottom, we have high pressure. So what's going to happen to the airplane? It's going to take off. It's going to float. When the plane about to land, if next time you're flying, they put this piece of metal in the back straight up, and that's the brakes. And what that does slows the flow of air over the top. Once you slow the flow of air over the top, that becomes high pressure on the top, and the plane starts to drop. When they go to take off or landing too, if I have a short runway, I want to take off on a short runway, we lower what we call the flap. On the back, there's a flap that hangs down. There's 3 settings on them. I lower the flap all the way to the bottom because I want the wind to hit that and die there, stop there, to make sure the plane rises quickly. If I have a short runway, I don't have that much room to go pick up speed and go take off. I need to take off quickly, so I'm going to slow the wind and the wings as much as I can below the wings. And I'll drop the flap all the way to 3, which is, I think, like 18 degrees, 19 degrees. So the flap is like this. When the wind hits them, slows the wind under them, and the plane rises much faster than when you have a long runway. It's called short feet takeoff there. That's what I have to do. You can use that logic for people with bad circulation. What happens if you have blockage in your system there? You got blockage here now. You got this buildup in your body there. You know? Now that blood here coming in, let's say I'm moving at 1.3 meters per second like that water, suddenly through this is moving what speed? 19.2 meters per second. It's like a pressure gun. Well, what happens as it goes through that? Well, if there's a loose clot here, a loose one, and you're moving at 19.2, and you hit that one, what's going to happen to that clot? It's gone. It's going with you all the way. Hopefully it doesn't go to your brain. Because if it does, you just had a stroke. So we got to make sure now that's open there. Again, you're laying in bed, you're standing up. Well, there's not much difference in height because we're not that tall people, but you take a hose now to a second, third floor to wash the windows, there's a change in height. We didn't deal with change in height. I wouldn't derive the equation. I'll put the equation instead of going through the math. When you have a change in height there, and I'll do a combination in a minute, and if I do a change in height without changing the size of the hose, I'll give you both cases. So the hose still the same, but we have a change in height of h here. We have pressure 1 here. We have pressure 2 here. We have a change in height. The equation becomes pressure 1 plus rho times gravity times height 1 equals pressure 2 plus rho times gravity times height 2. So it depends what you use for reference. If you use this as reference, height 1 is 0, height 2 is going to be h. And what happens if you have a combination of both? Meaning what? You're going to move that hose up to the second floor, but you're going to use that nozzle. And now you're going to put the nozzle at the end. So you got here change in height and change in size there. Then the equation becomes pressure 1 plus rho gravity times height 1 plus 1/2 rho V1 squared equals pressure 2 plus rho gravity height 2 plus 1/2 rho V2 squared. This is change in height only. This is change in height and speed, which means the size. What do we call that one? Change in speed, we called it? Change in height and change in speed. That means the shape of a change here. The size change. So that's the equation we use. And we'll show you where we'll use that. This is really Bernoulli's equation. That covers all of them. If there is no change in size, that means the volume is the same, it will drop out. If there's no change in height, these two will drop out. So that's really, when you talk about Bernoulli's equation, people refer to this one. And the other two can be eliminated just through the math. Let me quickly talk about when you have a tornado. They go, a tornado is coming, watch out. And you see the roof of a building just disappears. What happened to it? We talked about the wings of an airplane. It's designed to slow it down so you have high speed, low pressure on the top. The thickness of the wings of the airplane, not much of a difference between them. So if we look, we'll do the airplane first. Let's say we can make the velocity of the wind on the top 120 miles per hour. Just an example here. But the velocity on the bottom here, we can make it 100 miles per hour. Bless you. The wings of the airplane, they're not that thick there, so there's really not much difference in height. We can neglect that. Bernoulli's equation says the pressure on the bottom plus rho gravity times height 1 plus 1/2 rho V1 squared equals pressure 2 plus rho gravity times height 2 plus 1/2 rho V2 squared. Let's call the top 1 the bottom 2. So we have pressure 1 here, we have pressure 2 here. Since there's not much difference in height, since H1 is approximately equal to H2, we can drop that 2 pieces here. It's not going to make much of a difference. So the equation becomes pressure 1 plus 1/2 rho V1 squared equals pressure 2 plus 1/2 rho V2 squared. Pressure 1 plus, I don't know what pressure 1, never gave you pressure 1, but that's okay. 1/2 rho for air is about 1.29. V1 squared, that's 120. Let's convert that to meters per second. 120 divided by 2.24, 53.6. This is roughly 34.55 equals pressure 2 plus 1/2 rho, which is 1.29, velocity 2, let's convert that to meters per second, 100 divided by 2.24, 44.6. square it. I think I forgot to square that number, right? I'll come back and look at it. I forgot to square that number. I think 53.6 times 1.29 divided by 2, 1853.1. Looks too small. 1853.1. What is the change in pressure between P2 minus P1? P2 minus P1. 18531 minus 1285.5. P2 minus P1, or the change in pressure between the bottom and the top. The bottom is more than the top, bigger than the top, by the amount roughly 567.6. That's Pascal. That's the change in pressure. Well, next time you fly, look at the size of that wing. How big that wing is. That wing looks like this, the plane. It goes probably, just guessing there, approximately probably 30 meters long. Huge. It's not a short one. The width of it, I don't know, let's put some numbers. Let's say 10 meters. Treat it as rectangular shape, 30 by 10. So the area of that wing, 30 times 10, what? 300 meters squared? Guess what the force now? What is the force equal to? What is it? Pressure equals what? Force over area. Pressure equals force over, or force equals pressure times area. So the change in force is the change in pressure times the area. The change in pressure is 567.6 times the change in the area, which is 300, or the area, and that's the change in force on one wing, just one wing. And you have a force of 1702678 Newton. Roughly that's equal to what? 170,000 Newton on one wing, pushing up. And you got 170,000 Newton on the other wing, pushing up. That's exactly the reason why the roofs will take off, the roof of a house. Because what happens as the wind comes over the roof of the house, I'll use that actually in a minute. When you look at a house, we'll say the house is, I don't know, a ranch here. There's the door. And let's say it's, I don't know, 30 feet long by 20 feet wide. That's 600 square feet. Small house, very small. And now you get the wind coming. The wind is gusting 80 miles per hour. Well, 80 miles per hour is how many meters per second? 80 divided by 2.24? 35.7 meters per second. Bernoulli equation says pressure 1, that's what the inside is 1. Pressure 1 times rho gravity height 1 plus 1/2 rho V1 squared equals pressure 2 plus rho gravity times height 2 plus 1/2 rho V2 squared. Now we're talking about the roof of the house. There is not much of a difference in height between the inside of the roof and the outside. We're talking about a foot. Top, a foot. Trust me, that's not going to make any dent in that number. The roof is not even a foot thick. So between the inside of it and the outside, not much difference in height. So that's not even a factor. Pressure 1, inside. Now, the worst thing you can do when there is a hurricane or tornado is what? Close your windows. Because if you close your windows and your door, what's the speed of the wind inside your house? How fast the air is moving inside your house? It's not moving. 0.
Is 1.29 a constant?
Yep, for air. That's density of air. Pressure 2 plus 1/2 1.29 times the speed, which is what? 35.7 squared. So that's a 0. What's P1 minus P2 here? P1 minus P2, again, this is 0. Square that times 1.29 divided by 2. It's 822.7 Pascal. Assuming it's a flat roof, assume this is a garage or a shed, a flat roof. So the area of that roof, we'll convert feet to meters. What's a foot? How many meters in it? A meter is 0.3, or a foot is 0.305, I think, is it?
1 meter is 3.281.
Or 1 foot equals 0.305?
1 foot equals 0.305.
Yep. So let's convert that by multiply by 0.305. Convert that to meters. 30 times 0.305. That's 9.15 meters. And the 20 times 0.305, that's 6.1 meters. So the area is going to be 9.15 times 6.1, which is 55.8 meters squared. Force, or the change in the force, is the change in pressure times the area. The change in pressure is 827.7 times the area, which is 55.8. Ready for this number? 46,200 Newton. A big car like a Suburban is roughly about 1,200 kilograms, just to give an idea. 1,200 times 9.8. The weight of a Suburban is 11,760. So if we take 46,200 divided by that number, that's like parking 4 Suburbans on top of that little roof there. That's the pressure. It's going up there instead of coming down. Well, when you push pressure down, you get all these beams supporting you down. When you put the pressure up, you only get few nails on the top holding you. These nails are not going to be strong enough to keep the roof from just taking off and flying. This is like somebody pushing up, equivalent to 4 Suburban pushing down. That's how much force. And the roof will go flying. And that's the reason why, again, the roof flies. It's nothing because the wind picked it up. No. As the wind moves over that, it's moving faster. The change in the pressure, it becomes the pressure much lower, that the force from the bottom up pushing up is a very large force that the nails can't hold. So these are some of the applications for them. Other application, you've probably seen that perfume bottle, as you squeeze the air here, you blow the air, moves faster on the top, it makes the perfume rises through it, and it shoots out. That's the reason. Because the air on the top is moving much, much faster. That means low pressure, and the perfume is going to rise. We'll stop here.